Oh, I'm not entirely sure what question that might be referring to. Here, I can look it up here. Which worksheet was that? It is this one, chapter 4. Let's see.
Right there.
Oh yeah, there's a part in your notes where they tell you carboxyl groups form, when two carboxyl groups interact or something like that, they form something. It's one of those memorization things. I don't know it off the top of my head right now. Amino groups are able to react and form something. Cysteine residues form something. In fact, that one I remember. Cysteine residues, two cysteine residues interact with each other to form disulfide bonds, right? Somewhere else in your notes they tell you what these groups form. And those, that combined with these reactions here, the iodoacetate reaction and the cysteine reaction, you need to know those reactions for the exam.
Do you have to know like the mechanism, or just know what they form, or do?
Visually, if you can see a reaction, you don't have to draw it obviously, but if you see a reaction and you know what that reaction is, that's good. Know what they do for, you should know physically or reason what iodoacetate does. And what I don't have it on here, but let me write it over here. Here, let me write it on the document here. What iodoacetate does, and I am skipping a little bit ahead here, but while I'm on the topic, I think this might be in chapter 5 also. Know what iodoacetate is used for, and know what mercaptoethanol is used for. I think that one is in chapter 5. Know what they are used for. And what I mean by used for is that iodoacetate is used to block sulfhydryl groups. And I'm going out of order, my bad. The first thing that you should know is mercaptoethanol. And that is because when you are sequencing proteins, you know how in chapter 5 you're supposed to sequence an unknown amino acid sequence? One of the first things you do is you treat it with mercaptoethanol, and the reason why that is that mercaptoethanol is going to break all those disulfide bonds. So the role of mercaptoethanol, and you can find what it looks like in the notes, is it'll break disulfide bonds. After that, immediately after that, they treat that protein with iodoacetate, and that is because iodoacetate blocks those sulfhydryl groups and prevents them from just coming back together into disulfide bonds. So that is what iodoacetate does. Iodoacetate is in the cysteine reactions part in your PowerPoint notes, right by Ellman's reaction. I don't know what it looks like off the top of my head. Yes?
So for the mercaptoethanol, does that break inter and intra-disulfide bonds?
Yep, any disulfide bonds it's going to break.
Why does iodoacetate, does it have to react with cysteine? Or
the only one iodoacetate will react with, at least in the context of this class, will be sulfhydryl groups, which only cysteine has, is sulfhydryl groups. Yes?
What does iodoacetate do again? It blocks what?
So after mercaptoethanol breaks those disulfide bonds, you leave behind SHs. Iodoacetate comes in and removes that hydrogen and puts in this obnoxiously large functional group to where that SH was. And it's blocking it and preventing those sulfurs from coming back together to form a disulfide bond. That is what iodoacetate does. Yes?
So for when you sequence a protein, you first have to treat it with mercaptoethanol,
Yeah.
and then you identify the N and C terminus.
Yeah, and technically either of those two things can happen in whatever order. You don't have to know that for the exam. I'm just describing to you what happens. No, you don't need to know the order of those steps. No. Yes?
So typically, like for our class, would be mercaptoethanol, iodoacetate, then Edmond's reagent.
Edmond's reagent for context of sequencing. And there's also a reagent called Ellman's reagent, annoyingly sounds similar. Ellman's reagent, you only have to know that that's a cysteine reaction. So if you have an amino acid sequence that reacts very strongly to Ellman's reagent, that's a shortcut way of knowing that that amino acid sequence has a bunch of cysteines in it. That's all. Yes?
For the mid-hydrogen test, so the more prolines it has, is that like, there's something like, so it's a stronger test, the more prolines?
Let me clarify that also. So ninhydrin test. In fact, ninhydrin test fails when there is proline. So that's the crazy thing there, is that ninhydrin turns purple if there's lots of regular amino acids with regular amino groups at the end of them. And I think ninhydrin turns like yellow or something if there is proline and only proline. Will it do that? Okay. Yeah, yes, at the end of the structure, yes.
Do we have to know about like that CU test or the Buret or
Oh, no, not for the exam, no.
You want to know Elman's, Edmonds, and then Hydrin?
Yeah, so let me list them. You need Elman's, Edmonds, ninhydrin test. Okay? Elman's, Edmonds, ninhydrin test. For those fancy named tests. Okay. We unfortunately we're jumping around a little bit. Some of that is chapter 5, some of that is chapter 4, I believe. Yes.
Edmund just tells you the N-terminus?
Yeah, so we'll get to an example of that in a little bit. Okay. Yeah, all right, now back on track here. Okay, so we figured out how to answer isoelectric point and charge of an amino acid. Let's do a real quick one. We do the same thing, but we do it for a peptide, okay? We're trying to figure out the charge and the isoelectric point of a peptide. So, I guess I'll make up one. Aspartic acid, alanine, and arginine. Okay. All right. We have 4 amino acids here. It's a tetrapeptide. They may ask the same questions of what charge will this peptide have at some pH, and what is the isoelectric point of this peptide? In order to answer either of those things, I highly suggest you draw a charge diagram for that peptide. You will have to do something slightly different in order to draw the charge diagram. You need to draw out only the functional groups that matter. And what I mean by functional groups that matter is only draw out functional groups that have a pKa associated with them. Here's what I mean by that. Anyone remember what the side chain is for alanine? It's a methyl group, CH3. You go look in the pKa table for alanine, you will find out that alanine does not have a side chain pKa. So for the purposes of the charge diagram, I don't care about alanine. It doesn't have a side chain pKa, so I don't care what it looks like. ASP stands for aspartic acid. It is an acidic amino acid, and it does have a side chain pKa. Acidic amino acids are going to have a COOH somewhere down there. So I'm not going to draw the entire side chain. I'm only going to draw in the functional group that matters, the thing that will have a pKa associated with it. Both aspartic acids will have carboxyl groups in their side chain. Arginine is a basic amino acid. All basic amino acids in some form, whether cyclic or not, it doesn't matter, have an extra amino group in its side chain. Basic amino acids have an extra amino group in its side chain. Okay, so these are the functional groups that matter. I'm missing 2 more, and always remember to include these, is that the very first amino acid in a peptide is going to have an alpha amino group attached to it, right? And the very last amino acid in a peptide is going to have a carboxyl group attached to it. Okay, that's why we call the first amino acid in a peptide sequence the N-terminus, the nitrogen terminus. It contains this amino group. That's why we call the very last amino acid the C-terminus, the carboxyl terminus, because it has the extra carboxyl group there. Yes?
For
Arginine or aspartic acid? ASP for aspartic acid, yeah. For ASP, aspartic acid. Yeah, be careful that asparagine doesn't have it. Yeah, be very, yeah. Okay.
ASN, right? Or
ASN, yeah, it's a little annoying, but ASN is asparagine, which doesn't have a side chain pK. So that goes back to memorizing your 20 amino acids. Okay, these are the functional groups that matter. Each one has a pKa associated with it. Some we already know, and some we have to look in a table for. I already know that the alpha amino group is going to have a pK of approximately what? 9. The alpha carboxyl, jumping ahead there, or the alpha carboxyl group is going to have a side chain pK of 2, exactly. I don't know the ones on the side chains. I go look at a table. I'm probably going to write the wrong ones here. I'm just going to write numbers. It does not matter what they are. You will go look at the table yourself. 3 point something. All right. Whatever it is, you write it down. For arginine, I think it's like 10 point something, right?
Yeah.
10.5. These will be wrong numbers. I'm just doing this for illustrative purposes. You write down the pKa for whatever the side chain functional groups these are when you go look in a table, okay? Now we've written down all our pKa's. We've drawn in all our important functional groups with all of their hydrogens. Whoops. we can figure out what all the possible charges this peptide will have. I always draw the peptides and the amino acids with all of the hydrogens, with none of them missing yet, so I know what the maximum positive charge this thing could have. And it looks like the maximum positive charge you could possibly have is +2 from these two amino groups here, right? All right, that's the maximum positive charge this peptide could have. How many possible drops in charge could it have? The answer is, how many pKa's does it have? 1, 2, 3, 4, 5. I'm going to draw in 5 arrows. 1, 2, 3, 4, 5, because they represent each of these pKa's here. And each arrow represents a single drop in charge. And it goes all the way to -3. So this peptide has a wide range of charges between +2 and -3. And each one of these arrows represents a pKa. We can label each of these arrows with their corresponding pKa's. And when I draw it like this, you always go from lowest pKa to highest. Whenever you draw it, you should draw it like this, where it's the most positive stuff to the most negative stuff. It makes it easy to put in the pKa's because it's just from lowest to highest. So 2, 3.7, 3.7, 9, and 10.5. Those are the pKa's we've written up here. They go in their respective spots down here. Okay? All right, so now we have our charge diagram for this peptide. You can do this for any peptide of any length. Bottom line is you should get to this point because it helps you answer the following 2 types of questions. What charge does this peptide have at a pH of 7? -1 is the answer because, as we look in our charge diagram here, where does 7 belong? 7 belongs between 3.7 and 9. This peptide has a charge of -1 at a pH of 7. Okay. And, you know, at a pH of 13, this peptide has a charge of -3, exactly. Okay. That's one of the possible questions. The other question is, what is the isoelectric point of this amino acid? And I realize I messed up here because this doesn't make any sense. Well, actually, no. Never mind. Ignore that last part. You can still do the math here. Well, the isoelectric point of this peptide is you pick the 2 pKa's that are surrounding the neutral form of this peptide. So here's the neutral form of this peptide. Here are 2 pKa's. I was overthinking it. It is simply this. 3.7 plus 3.7 divided by 2. The isoelectric point for this peptide is 3.7 when you type it into a calculator. Okay. And again, for future reference, and this works for any peptide, you draw out the charge diagram, and the isoelectric point is the average of 2 of those pKa's. The 2 that you pick are the ones surrounding the neutral form of that peptide. 1 second. Yes?
So this one technically wouldn't really have an isoelectric point because it would immediately go to -1.
It's one of those that actually in the lab, its isoelectric point would be at 3.7, but it'll probably change really quickly from +1 to -1 very quickly. Yes?
I don't want to confuse everyone, so you might want to answer me later, but how come we can equate pH to pKa?
You're talking about the charge part, right?
Yeah.
So,
anything, like, it's like, what's the, because you could just say the pH 7, and then you look and the pKa is 9, I don't understand how you
so the pKa is basically like a written, known variable for something. So pKa is like, you go look the pKa of phosphoric acid, it'll always be like that no matter where you are in the universe. pH is the environment. pH changes back and forth all the time. So they are related to each other by pH is a measure of the environment, and pK is measuring the thing that is in the environment. Yeah, so that's why you have formulas that relate them to each other. Like, well, the only one is Henderson-Hasselbalch, plus log of conjugate base over the weak acid. So basically the pH of the environment is affected by an established pK of the thing that you're looking at and how much of that thing you have.
Okay,
Yes.
that makes
So
sense.
that's what the relationship is between them. Yes.
Thank you.
This is actually in regards to the example that you did in the peptide. For the first peptide, like we crossed it out because apparently it didn't have a pH. But I'm looking at the chart.
Yeah, and I think I probably sent the email regarding that. Just go with, because I was working out just something I Googled off my phone. You always go with whatever the pKa table tells you.
So
Not,
it does have
I don't know off the top of my head. If it says it in the, and if you want to know what the pKa table looks like for the exam, I've said it many times, go open practice exam 1, go all the way to the end of it, that's the exact pKa table you will be given for the exam, okay? I don't memorize the pKa tables. Okay. We got charges, all that stuff is done, good.